Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email. As I think you know, these Tech Talks have been designed to provide straightforward insights into radio frequency components, the related technology, and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yes, thank you, Paul. So we are looking at basically talking about some of the mechanical differences between the different construction approaches, as well as the electrical performance differences. As I mentioned in previous Tech Talks, and I'm going to talk about today here really, is that the technologies all have advantages and disadvantages. There is no one really better technology, one over the other. The application, the frequency, the bandwidth, all these sorts of parameters all drive to basically determine which is the best technology for any one application. So in order to be able to make those decisions, you need to understand really what the trade-offs are between the various technologies. So there are 2 main categories of these sort of construction technologies that we use here at TRM. We use lumped element technology, which is a sort of individual component, transformer, inductor, capacitor sort of networks, as well as distributed technology, which is can be broken down to 2 main classes, strip line and microstrip. And basically what I'm going to talk about today is why would you choose one over the other for any kind of particular application, and really what are the strengths and weaknesses of each one of these technologies. We'll then have a quick summary and then talk about some of the TRM differentiators.
Okay, well, that sounds good, Shaun. And maybe to get started, are there some major differences between lumped element and distributed technology?
Yeah, I mean, from a mechanical standpoint, they're quite different. Lumped element technology uses discrete components to make all the circuit elements. And these are the traditional sort of things that you think about when you think about an electrical circuit. These are wire-wound transformers, inductors, capacitors, resistors. These are individual components strung together to be able to build the sort of classical kind of networks that you think of when you think about circuit design. Distributed element technology, on the other hand, uses a series of transmission lines, and these are just lines of a specific length and a specific impedance, and the length and impedance and the way that they're interconnected creates the circuit elements. So the circuit elements are not individual components like you think about. The circuit elements are actually the PC board itself and the circuit that's printed on it. So we make effectively capacitors, inductors, and other devices by printing transmission lines onto PCBs. The interconnection of these lines and the way that, and the impedances and the length of the line are all frequency dependent operations that really affect the way that the line interacts with the frequency that's hitting it, and that is the way that those sorts of circuits operate. There are no discrete components on those circuits. The circuit board itself is the circuit. And that's really the main difference between a lumped element technology and a distributed technology, whereas a lumped element technology, we're talking about sort of classical kind of components that we're going to solder onto a PC board. The PC board is more or less just connecting points for those circuit elements, whereas for distributed technology, the board itself creates the circuit elements and the interaction that we're looking for by printing various shapes and configurations of transmission lines to be able to form that. And those are really the two main types of technologies that I'm going to talk about today.
Okay, and you said a little earlier that one is not necessarily better than the other. So should I assume, or should we assume, that there are some specific reasons why one might be a better choice versus the other?
Yeah, absolutely. And basically, they do offer very different advantages to each other. I want to say here that neither one is inherently better than the other, although what you will find is that one will generally operate more efficiently at some frequency than another. And in general, what we have is we have some frequency dependent parameters that kind of divide this these two camps into whether or not you would use a distributed technology versus a lumped element technology.
Okay, then maybe as the question that you posed here in the last bullet, what differentiates the two, maybe you could start out by sharing more of the details about lump technology.
Absolutely. So lump technology is a technology, like I said, where you have individual elements that you either buy or make, and then solder to a PCB as connecting points. These devices use wire wound transformers. The transformers are typically wound on ferrite beads, and these sorts of components use RF transformers as one of the main building blocks for building either a power divider or a directional coupler. The advantage of these sorts of devices is they have extremely broad bandwidths. 100 to 1 bandwidths for some low to medium power devices are very common. Electrically, we refer to these as all-pass networks, and that theoretically, if you were to go into your analysis software and put in a transformer, you would see that this transformer would operate from virtually DC. You need some frequency for a transformer to work, but very low frequencies, all the way up as high as you can, for as big a number actually as you can think about. From a theoretical standpoint, these are extremely broadband devices. Being practical about it, the bandwidths are really limited by inductances that you can generate on the transformers, and that usually sets the low end, the low frequency of operation by what the inductance is of the transformer, and the high end is really limited by how neatly you can wind that transformer and how you can mitigate interwire capacitance to make sure that you don't end up with a resonant LC network, which would limit the high end of that network. So what you have now is you have a theoretical infinite bandwidth device that is limited by two parameters: the inductance, which sets the low end, and the interwire capacitance, which sets the high end, and the interaction of those two. By being smart about designing transformers, like I said, we can get very broadband source of devices out of these sorts of devices. Another component that does limit what we can have for a high end on these devices also is a capacitor self-resonance. That is also an important parameter that we have to watch out for as we are designing these sort of lumped element technologies. So a big advantage of lumped element technology is that it has extremely broad bandwidths. Its sort of limiting factor is the fact that we have to watch at the self-resonance and parasitic capacitance of the individual elements that we're using to make this technology. What this does is it limits basically the higher frequencies are where these parasitics become unmanageable. So lumped element technology tends to be a lower frequency sort of realization of these circuits. And like I said, with low frequency operations, lumped elements are a great solution. They perform well. Since they are all pass networks, they actually work very low in frequency, and they really physically aren't that large. As long as the inductor that you're building is high enough to give you the required X sub L to have the transformer work in a transformer mode as opposed to an inductor mode, little above the what I was planning on talking about today. But as long as that parameter is met, you can build very small transformers by going to higher permeability beads that work very low in frequency. So this can be a very compact technology and work over very broad bands. Really a nice solution as long as the frequency does not get too high.
So what happens if the frequency exceeds the upper limit?
So once and the upper limit is really typically around 2 gigahertz. Sometimes we go up to about 3 gigahertz depending on the individual circuit. But really, what happens there is that the interwire capacitances and the stray reactances for the transformers really start to become unmanageable. And so what happens there is we do get a high frequency cutoff of these devices somewhere in the 2 to 3 gigahertz range. So an interesting thing of note here is that you can achieve very high power handling using ferrite technology. What happens though is when you get higher in power, you physically need to get larger beads to dissipate the heat. And when that happens, what the capacitance of those longer wires starts to react more with each other, plus the stray inductance of those wires becomes a little bit more unmanageable as those beads and capacitors get larger and larger and larger. So what happens there is now you're starting with the same very broadband basic network, but because the parasitics of those larger transformers are higher, you have reduced bandwidths. So a high power bandwidth might only be a 10 to 1 as opposed to 100 to 1. Or if it's a very, very high power, maybe the bandwidth is even reduced more than that, because you have to manage those parasitics within those individual component designs. But you still can get a very compact, relatively compact design using these sorts of transformers over the other technology that we're going to be talking about in a few minutes, which is the distributed technology.
Okay, so that's a lot of information. Maybe before we do get to that distributed technology conversation, you'd like to summarize the pros and cons specifically for lumped element technology.
Sure, lumped element technology is inherently broadband. I mean, the math for a lot of these transformers are all pass sort of networks. There are some exceptions, but a lot of them have very, very theoretical, very broad bandwidths, really limited by the parasitics of the individual components themselves. We can build very, very broadband components, typically up to say 2 or possibly even 3 gigahertz. These can be built in a wide variety of packages. We can build power dividers, we can build power combiners, we can build directional couplers, we can build 180 hybrids, we can build 90-degree hybrids. All of those components that TRM builds can be built using lumped element technology. So it is a very flexible sort of technology. And like I said, for very good performance in very small packages for frequencies below 2 gigahertz, it's a fantastic technology to use. There are a lot of advantages to it.
Okay, so now what are the details associated with distributed element technology?
Distributed element technology are based on transmission lines, most notably quarter wavelength long transmission lines. There's some things that happen mathematically at a quarter wave that allow us to create a bandpass structure as opposed to an all-pass structure. So mathematically, these are band limited devices once we go into distributed technologies. We can build out of a transmission line the same networks that we can build using distributed technology. We can build power dividers, we can build power combiners, we can build directional couplers, we can build hybrids, we can build both 90-degree and 180-degree hybrids, all using printed technology. The sort of negative, if you will, of using transmission line technology is twofold. First of all, if we're based on quarter wavelength long lines or multiple quarter wavelength long lines and stepped impedance sort of transformers, if you can imagine, if a wavelength is 30 feet long, which is something that you're going to get down at HF frequencies, A quarter wavelength long is still 7 feet long. Building a device with 7 feet of cable in it is a little unwieldy. So therefore, instead of having a high frequency of operation like we have in the lumped element technologies, we have a low frequency of operation, really that makes where these devices start becoming practical. And so that is one of the limits of going to a distributed technology, is that you have to deal with very long lines for very low frequencies. However, once you get up into the upper microwave in the gigahertz range, quarter wavelength longs become very efficient because the wavelength starts getting shorter and shorter and shorter, and we can build some really nice parts in the gigahertz range frequencies. So therefore, really distributed technology we start becoming effective at somewhere around 200 megahertz, 300 megahertz, 500 megahertz, somewhere in that region, depending on the bandwidth that we're looking for. And you can go right up through 100 gigahertz for this technology. It is really a very more of a higher frequency sort of applications tend to use this. The other thing also that is different from lumped element technology, instead of it being an all pass sort of design, these devices tend to be band pass designs, which means that there's a definite upper frequency and a lower frequency. There are some exceptions where we make high pass structures, where we start running into limitations of the high pass, again with moding happening, that sort of limit the high end. But there's definite advantages to distributed technologies that are certainly different than what we have for lumped element technologies.
Okay, and as I recall from your slide on stating objectives, I think that there are a couple of different types of distributed element technologies.
Yes, there are, and there's really two main types. Now there are more. I mean, right now all I'm going to talk about today is microstrip versus strip line. You also could go into other variations of strip line. There is suspended strip line, coplanar waveguides. These are all printed technologies that use distributed technology, and there are several more which I'm not going to get into today. The two main types really are strip line and microstrip. Strip line is think about strip line as being a covered balanced line. So this is a transmission line that lives between two ground planes. This sort of propagation is very nice. Mathematically, it's very well understood, and it creates something known as a TEM mode propagation. So what it is what that means is that the wave, the field coming off of the line is symmetrical. And this is very important when we think about applications of a strip line as opposed to a microstrip line. A microstrip line only has one ground plane. There's a ground plane under the transmission line itself. It is what we refer to as an unbalanced line. The downfall, being a non-TEM mode propagation, is that there is some frequency dispersion. And what frequency dispersion is that the time that it takes for a signal to go down the line will vary with frequency. Unlike a strip line device where you have a balanced mode, when the field is balanced, it means that it is symmetrical. And when it is symmetrical, the field is in the same medium going to both ground planes at the same time. What this does is it allows for the propagation time to be independent of frequency. Microstrip, on the other hand, some of the field is in air and some of the field is in the dielectric. And when this happens, what we have is an unbalance of the field, and that unbalance is frequency dependent. So that is a downside of microstrip. Now, the upside of microstrip is that it is much easier to manufacture. So what we tend to do is use the best of both of these worlds. For strip line, we use strip line for designing directional couplers because the fields are symmetrical. And we'll get into a little more detail as to why that's good. Hybrids and phase shifters, whereas microstrip, where we're less concerned about frequency dispersion, with the performance of the device, microstrip is a very cost-effective method for building things like power dividers. So why is strip line better for couplers than microstrip? It has to do with, in order to get say we're building a directional coupler, and we need to make sure that we have good directivity for that directional coupler. What needs to happen is the energy that is being coupled across, there's a cross coupling that happens there, and the energy that is coupled across needs to be phase canceled with the return energy on the main line. That only happens across a broad band of frequencies if the propagation mode is equal across the frequency band. So what that sort of limitation does, and that only happens in a strip line device. Going through those sorts of devices, strip line becomes a necessary item in order to be able to build broadband directional couplers that have good directivity. It's just an important piece that sort of limits microstrip. Microstrip can be balanced over narrow band frequencies. There are some tricks that we do when that becomes necessary, although most of the parts that TRM builds are broad enough band where it really isn't practical for us to build that way, and we tend to go ahead and build all of our couplers, hybrids, and phase shifters in strip line to make sure that we have that good TEM mode propagation in order to get really good directivity performance.
Okay, well, once again, lots of information. Maybe as you did earlier, you could summarize the pros and cons specifically associated with distributed element technology.
Absolutely. So basically, strip line technology and microstrip technology, because of the length of the line, so we're looking at coming in there with quarter wave long sections, or if we're looking at a tapered line construction, sometimes these sections need to be 3/4 of a wavelength long at the low frequency of operation. Really, low frequency becomes impractical just due to physical size. These things become enormous if you try to do it at lower frequencies. And so really the practical low end cutoff tends to be around 250 megahertz as far as to what we can do for distributed technology. The technology is great. It's very repeatable. We're talking about PCB, machine-based manufacturing, where we're laser direct imaging images onto panels and chemically etching them. So we get very, very good sort of repeatability from that process. Most of these networks have a band pass, or sometimes we do have a high pass frequency response for these networks. And like I said, there are lots of advantages to distribute technology for higher frequency type components. And like I said, it's a really there's a lot going on. It's a good technology. And realize that within the distributed technology, there are lots of subcategories that we certainly can delve into, each one having their own advantages over the other.
Okay, great. So maybe to make it easier for people to take what are the key takeaways that you'd like to summarize for the whole session?
Sure. So the overall thing here really is we have to look at each requirement. We have to look at frequency of operation, and how big of a part room does the customer have to use this part, plus also how much room are we going to be allocating for this. And once we have those couple of things, that leads us into whether it's lumped element, if it's a lower frequency part, or higher frequency parts tend to be distributed. Now, there is an area of frequency somewhere between UHF, VHF, and up through L band, where we can use either lumped element or distributed. And in that region, TRM really excels because we can mix technologies. Sometimes there's a printed transformer that will give us lower insertion loss in that frequency band. But we want the better isolation, for example, of using a transformer for the output for the divider for the two-way. So there are a lot of things that TRM does with mixing technologies between printed or distributed technologies and lumped element technologies to sometimes get the best of both worlds. And very often, the customer's end package will determine in those frequency ranges of UHF through L-band, as far as to which technology we actually do use here at TRM. Size becomes an important parameter, as well as power, thermal dissipation, all of those sorts of things all play in to that decision.
Okay, and finally, maybe springboarding off that final comment, how would you say TRM microwave is unique in applying these technologies? What are the differentiators?
This is really, what we do is, we love to talk to customers, and that's really the advantage here with working with TRM. We don't have just one technology, and I think that that's important for people to realize. Every technology has pluses and minuses. There is no best technology in the world. Certain things are better for others. Even some technology you may think may be old-fashioned. Some of that technology works fantastic at doing certain jobs. And TRM is very happy to use some of that technology, as well as the latest technology as well, to be able to go through there and really design the best part for your needs. TRM really prides ourselves on developing unique, robust packaging and also testing. We have a very robust test engineering department here at TRM, happy to give full evidence of compliance for all of our designs and components. TRM, again, we like to think of ourselves as being a solution provider that also supplies parts. And working within this passive space, there are lots of options. We like to go through and have the discussion with our customers to come up with the best solution possible.
Well, certainly a lot of the information you've shared during these tech talks would support that position. And I think we have time for one question today, and we do have one here. The question says, I understand that some people design couplers using microstrip technology. What are the limits of those components?
Yeah, as I sort of alluded to a little bit in the talk earlier, microstrip does not do well with coupled lines or building directional couplers. And that has to do with the fact that the even and the odd mode propagation for a coupled line, they have different velocity factors when you're in microstrip. In strip line, coupled lines, the even and odd mode have the same velocity factor. Therefore, you get good cancellation back at the terminator port, and therefore good isolation. What you can do in microstrip is you can fool the wave over certain frequencies, and there are various techniques that are used. There is a sawtooth sort of construction that can be done to help change the length of one mode over the other. The other thing you can do also is you can add some capacitance at the right at the end of the coupler to help, again, to rebalance those modes. Other people, for example, with Lang couplers, will go in there, and it is essentially a multi-section microstrip coupler that is built. The mechanical layout of a Lang coupler also adds some needed added capacitance at the end of each line, again, to help balance the even and odd mode for those devices. Now, the balancing can be done. However, it is very narrow band. Most applications only tend to be 5% bandwidths, in those sorts of things. You can develop Lang couplers to go up to say 20% bandwidths, but that is really probably about the limit as far as what you can do. There has been some work done to show a little bit more bandwidth than that. If you really work hard, you might get it up to an octave, but that's really the limit. Here at TRM, most of our components are multi-octave sort of devices, and really, using microstrip as a propagation mode for those sorts of devices is really beyond the limits of physics, because of the propagation errors that you get between the even and the odd mode. I said it's unfortunate. Like I said, some people, if you're dealing with a device where you only have a very narrow bandwidth, or say you're only working at baseband, and you can utilize a very narrow band coupler, then you can do it in microstrip. It takes a little bit of work, but it can be done. Like I said, most broadband devices that are built are all strip line, because of the balance mode, it really just eliminates that entire even odd mode problem.
Okay, well, thank you, Shaun. As always, nice job. And thank all of you for joining us today. If you are a customer and you have more questions, or if you'd like to discuss details with one of our engineers, we'd love to hear from you. And please feel free to call out the engineering hotline. The number is on your screen, 888-677-6877. There are no costs for these calls. And if you're one of our field representatives, then of course, you know your calls are always welcome too. And you can also submit questions directly through the sales rep portal on the website. This will be our last Tech Talk this year. We'll take the holiday season off, so we'll hopefully look forward to reconnecting with all of you in January. Thanks again, and thank you again, Shaun.
Yeah, thank you, Paul.